And good morning, friends. Um, Welcome to the beginning of week 3. We've got a couple of things going. I'll get PLC 3 posted later today. I'm still converting it into a quiz format for you. Um, and that just takes time because it does. Uh, Homework 2 I posted on, I don't know, Friday, Saturday, something like that. And that's going to be due Wednesday, the 26th. So not tomorrow, but a week from Wednesday, 2/26. And lab 2, I also posted that on, no, I didn't post it on Friday. I posted Saturday. So sorry about that. Family had a Valentine's Day thing. So I hope that you all took care of your loved ones and had a happy Valentine's Day and a happy President's Day and a happy other President's Day and whatever else there is going on around here. Anyways, Lab 2, because of the later post, will shift the due date also to Wednesday, but that's this Wednesday, not next Wednesday. So that's tomorrow. Okay, so that's Wednesday, the 19th. And as with normal operations, we have plus quiz here on the homework. So whenever homework's due, we have a quiz. That's kind of standard operating procedure. So that's what's on the schedule of uh, of things for the next week or so. The homework you'll find has thermal expansion. It has some ideal gas stuff in it, and a kind of a van der Waals, a nice little fun van der Waals problem, which is an extension to the ideal gas, so that we know that the ideal gas is a nice model. There are also other models, and the van der Waals is the first easy model that takes into account condensation of a gas, whereas, of course, ideal gas doesn't. Um, so I believe we were finishing off with radiation last time. So let's just do that quickly and we will go from there, do an example and move into our next topic, which has to do uh with the intricacies of the ideal gas model. All right. So last time I was talking to you about heat transferred via radiation. Okay. And uh, and we've got quite a bit of glare here, so let me see if I can fix that. But I'll just keep talking to you in the meantime. So radiation, of course, I mean electromagnetic radiation, which is infrared, visible, UV, all that. Hopefully that's helped. Oh yeah, that's helped. Okay. So I'm talking electromagnetic radiation, and I told you that the Stefan-Boltzmann law was the thing that helped us out with calculating how much radiation is emitted uh, by a body, right? The Stefan-Boltzmann law is related to the idea of black body radiation. Now, black body radiation is a theoretical construct, and we will talk more about this during the section on early quantum mechanics, which will come more towards the end of the semester, the final third. But the black body problem was a big problem. It was an idea that since everything above 0 Kelvin radiates, we want to find out how much does it radiate. And so there were a couple of attempts to try and find out how much it radiates. And what eventually happened was classically that they calculated that anything that had a high enough temperature would radiate infinite amounts of energy. And of course, that's absurd. And it wasn't until Max Planck came along, and I'm going to go for around 1910 here. Well, it was around 1900, but it was 19 between there and 1910 that he basically derived the correct black body spectrum, or the black body curve, the correct black body curve, and that's what I drew up for you on the board last time, which was the idea of something like an intensity, which, by the way, is not really what it is, but I'll just call it that. And this, I think I said, was frequency, and frequency, that's the frequency of the radiation that's emitted by the warm object, right? And so we came up with these curves that look kind of like this, and this is for a given temperature. So temperature, say T1, okay? If I had a lower temperature than that, then the curve actually does a couple of things. Number one, the peak shifts, okay? So right now, the peak of radiation would be here. This is the most intense. It's the most amount of radiation emitted at this frequency. Okay. That's not to say it's not at others. It's just the most is emitted at this one. And that's characteristic of the temperature. Okay. Now, number one, the curve, as I lower the temperature, the curve shifts back this way, meaning that I am giving off less frequent electromagnetic radiation. And that means, if you know your spectrum, that means that it's basically moving, oops, forgot the G. It's moving into the red region. Okay, whereas out here you'd have UV, in here you'd have IR. So when the frequency is decreasing, you're going that way on the spectrum. Okay, when the frequency is increasing, you're going this way towards the UV blues and UVs. So when we say things become redder, that means you're going either towards red visibly, or even out of the visible spectrum, you're going towards infrared. You're getting less frequent. Well, I guess I should go that way, right? You're getting less frequent. When it's going bluer, it's getting shifted up towards the blue part of the spectrum, or even out of the visible spectrum into the UV. That's still referred to as being more blue. Okay. So as the temperature drops, it shifts back towards the red, it being the peak, and the area decreases. All right, so there's a lower frequency at the peak of this curve, okay, whereas this one is at a T, which is less than T1. Okay, so the area under the curve is less, and the peak has shifted. So I think you can understand if things cool off, it emits a it's a less energetic amount of light. So it's a more red, infrared, radio waves. It's a weaker energetic light. So that's the first thing. So for example, if this curve at T1 was, say, for example, the sun, then the frequency here would be indicative of a yellow-green color. I do not know what the frequency of that is, but I do know what the wavelength is. It's going to be around 500, 550 nanometers. Okay. Now, when I move back here and I lower the temperature, then the frequency drops. Of course, that means the wavelength increases. So I'm moving out here into the reds. So this could be, for example, something that is glowing red hot, whereas the sun is glowing yellow greenish hot. And then something that's glowing white hot is even further over. The peak would be over this way. And if I increase the temperature to that, it would have more area. And I think I drew that on the board for you last time. So, right, so this would be a situation where T would be greater than T1. The frequency of the peak has shifted over this way towards higher frequency, and there's a lot more area underneath the curve. Okay. These are known in general as the black body curves. Okay, these are black body radiation curves. Okay. Now, the two things that I was talking about, number one, that the peak moves was investigated by Wilhelm Wien, and he was Austrian, I think, or maybe German. Boy, I should know that, but I don't. Well, he's one of those two. And he figured out that the peak displaces as a function of the temperature. He figured out that if you have a higher temperature, you're going to be over here. If you have a lower temperature, you're going to be over here. And it fits nicely. The other thing was the Stefan law. Now, Joseph Stefan, who I think was Hungarian, but again, I can't remember. He experimentally figured out this law, and then Ludwig Boltzmann, who I'm pretty sure was Austrian, or maybe he was German. Sorry. No, I'm pretty sure he was Austrian. Um, nah, I don't know. He theoretically figured it out. So it's called the Stefan Boltzmann law because it was the experiment, the theory that figured out the law, which I'm about to tell you. Now, the law that they are talking about is related to the area underneath these curves. Okay. Now, we use the word black body because that's like I said, a theoretical construct in which it's an object which absorbs all radiation incident upon it. Okay. And that means it reflects none. And then it radiates perfectly based on its temperature according to this curve. Okay. So a black body with something that is, since it is absorbing everything incident upon it, appears, but it has no reflection, so it appears black. And then if it's radiating according to its temperature and the temperature was low enough, then you wouldn't be able to see it and it would be in the infrared, so it would be invisible to us, right? So hence the word black body. Now, the Stefan-Boltzmann law has to do with the area underneath these curves, and the area underneath these curves goes up drastically. As you can hopefully see, this is a small amount of area here for a lower temperature. For a higher temperature, we get the T1 curve. For an even higher temperature, we get the T greater than T1 curve. That area goes up quickly according to the temperature, and it was these two guys who figured this out. So the Stefan-Boltzmann law is the area underneath these curves. And it goes like this. Essentially, it says that the power radiated per area, okay? So in the same kind of way that we talked about the power per area in the conduction, this is also a power per area. It goes like this. It's a constant times another thing which kind of tries to approximate how good of a black body it is, times temperature. So essentially leave a little space here. And the first thing that we want to realize is this goes as T to the fourth power. Okay. T to the fourth means that it is heavily dependent on the temperature, right? It's quartic in the temperature. And that's why we get this drastic increase in the area under the curves as the temperature goes up, even little bits, right? Even small increases, and all of a sudden, right, if I, for example, double the temperature, I'm getting 16 times the amount of area underneath the curve, which means it has to get big quickly. Also in here is a constant to get the units right. This is known as the Stefan constant. And it has the value of 5.67 times 10 to the minus 8. Or no, sorry, 10 to the plus 8. 10 to the 8 watts per meter squared Kelvin to the fourth. Okay. Since I'm doing this, remember this has to be in Kelvin. This has to be the absolute temperature. The temperature will not be in centigrade. It will not work out for you if you put that in centigrade. It must be in Kelvin, and you raise it to the fourth. So yeah, you're talking about a number that's like 300 to the fourth. Okay. No, I did get that right the first time. It is a minus 8. Sorry, change that. 10 to the minus 8. 10 to the minus 8. let me just look at this. Am I right here? Yeah, it's 10 to the minus 8. And then I second guess myself. No, it's 10 to the minus 8. I'm correct the first time. Should have stuck with it. 5.67. And it's really easy. That's why it makes it easy to remember, right? 5, 6, 7, 8. And I mean, how great are these numbers? And there's also here a another number here which tries to tell you how good of a black body it is. Now, this epsilon number, I'm just going to take a minute to talk about that. Okay, this epsilon number is quantifying the black bodiness of it. Okay. So it's saying that if it's a black body, then this number epsilon is going to be 1. So we call that a perfect black body. And so what is it if it's 0? Essentially, it's a mirror. It's a reflector, right? Because if you're a black body, you are, by definition of the construct, you are absorbing everything incident upon you. And so we call that you are absorbing everything incident upon you. That's like 100%. If you are absorbing absolutely nothing incident upon you, then you are reflecting everything and you have become a mirror. Okay, so things that are more shiny are less of a good black body. Now, interestingly, you'd say, well, a black body, it should appear black. Well, no, the sun is a great black body. Okay, the sun's a black body because it's radiating based on its temperature. And that would be its surface temperature, not the temperature in the core. The and the sun isn't black, right? So you'd say, well, how come it's called that? Well, remember, okay, it's a construct by which we're talking about if there's radiation coming off it, it's based on its temperature, and it fits a black body curve quite well. And I think that's in fact how Stefan first started his investigations. But anyways, so 1, 0, it's just a number between those two, and it's this kind of mathematical formula here. And so if we wanted to figure out what's the total amount of power coming out of this body based on its temperature, all we'd have to do is then multiply the area, and that area would be the surface area. In other words, the radiating area, right? The sun has essentially a radiating area, but that would be the surface of its outside, its farthest outside, right? Not a cross section. It's the outside surface. All right. So if we solve for the total power radiated, by a uh, by a thing, right? The total power radiated would be then sigma times epsilon, and then a t to the fourth, where everything is the same, but this a, remember, is the surface area, not the cross section, surface. Okay. All right. Now, last time I gave you a bit of a teaser as to how we could possibly use this, and that comes to the age-old question, time immemorial. People have asked this since we became apes. What would it be like if we were ejected into outer space without a spacesuit? Well, maybe not since apes, but nonetheless, people wonder this. What happens if you are ejected, like in the uh what's the one? There's a couple of films in which stuff like this happens. Um Gosh, I can't remember if it was Star Wars or something else. You have to go from one to the other spaceship, and then they They threw themselves out the airlock. I can't remember which one that was. Anyways, point being here that if you are in outer space, then you are not losing heat via conduction. You are not losing heat via convection. You are solely radiating, right? There's nothing else there to take any heat away from you. So we can approximate the radiation of a person based on that by thinking about, well, what kind of black body number would characterize a person, about what their skin temperature is, et cetera, et cetera. Oh, and by the way, I think I mentioned this last time before as well. The reason in outer space, okay, we'll talk about this too, but the reason in outer space you're losing heat via radiation and you feel cold is because you're not receiving heat via radiation. Whereas in a room like this, remember, everything that has a temperature is radiating. And when I say a temperature, I mean an absolute temperature, so above 0 Kelvin. That means the wall is radiating, the ceiling is radiating, the desk, right? Not only is there all climate control also blowing perfectly equilibrated air into this room or whatever it's doing, I don't know. I'm also getting radiation from the environment. Even the air is radiating, right? So when you think about the net amount of radiation, that also goes by the same t to the fourth. And if you think about this, the net radiation of something, okay, the net radiated power would be that power thing that I just erased, sigma epsilon A. But when I think about the t to the fourth, that would be a loss of heat, right? So I'd have to have a minus sign on that one. Plus, I'd be gaining from everything else around me, and we'll call that the environmental temperature. So I'll call that T environment here to the fourth minus my temperature to the fourth. Okay, so whether this number of net radiated power turns out to be positive or negative depends on, am I receiving more than I'm giving off? Am I giving off more than I'm receiving? And then the sign of the net radiated power will let you know, is it a plus or a minus? Okay, so if you have something like this going on, then you know you can look at the environmental temperature and figure it out. Now, of course, in space, you'd say, oh, well, that number is 0. Well, it actually isn't completely 0. Space has a temperature, which you might be interested to know. But yes, there is a temperature in space, and it is due to the radiation that you would be absorbing, okay, while you're out in space. So it's low, okay, it's actually below 3 on the absolute scale. So that's good enough to ignore, especially because we've got these things to the fourth powers here. So I am going to ignore that ultimately here. All right, so here we are, we're in outer space. The in outer space, in out, or space example. So what would happen? And people say, oh, you freeze instantly. Because it's outer space and it's really cold. So you'd probably freeze instantly. Well, let's take a look. I'm going to go back to my net radiated power here. I'm going to say this is 0 in space. Or I'm going to say it is, it's not. I'll say approximately 0 in space. And so I'm losing, okay, I'm going to be losing heat. All right. So my net radiated power will be negative. Okay, so I'll just leave myself that note right there. And let's calculate the total radiated power as sigma epsilon A times T to the fourth. And I'm remembering that it's negative. I'm not going to carry the minus sign in right now. We'll deal with that later. All right, a couple of approximations as to what type of surface area. I'll just use myself as an example here. What kind of surface area am I dealing with? What would be my black bodiness? what's my emissivity, in other words, this epsilon, that's a constant, just gets a unit, right? So that's always going to be the same thing. So let's approximate. My surface area, I would say, let's just go for about 2 square meters, right? If you kind of, sorry, but if you took all your skin off and then laid it out and tried to measure about how much it was, it's probably about this. Maybe it's a little bit more, maybe it's a little bit less, depends, right? Okay, but I'll say it's about that. Um, let's suppose I am certainly not a black body. I do not emit, I mean, I do not absorb everything incident upon me. I do reflect, as it turns out, quite a bit. So let's go with an epsilon of about zero point 0.7. And you notice that in this calculation, it's not going to make a big difference. It's going to be, it could be like 0.5 or 0.2, and you're really going to be off by a factor of less than 10 anyways. So that's not that big of a deal. And we know that sigma is 5, 6, 7, 8, or 5, 6, 7 minus 8. Even that would be even better to remember it that way. So let's go see what we get here. If I calculate the radiated power, I'm going to do 5, 6, 7 minus 8. Well, I'll even put the units in here. Watts per square meter Kelvin to the fourth. I've got a 0.7, a 2, and a 4. So let's go 0.7. We'll go 2 square meters. That's going to cancel off that square meters. I'm going to get a Kelvin temperature now. What's my Kelvin temperature? It's probably room temperature, so I'm going to go 300. And that's going to be taken to the fourth power, which means that's going to end up being kind of a big number. But that's okay because we've got this -8 here, and that's going to help kill it off. So if I calculate all that stuff out, I get a number which is super duper, and it's about 640 watts. Right? My Kelvin to the fourth is going to go away with that Kelvin to the fourth, and I'm going to be left with watts overall, and that's a rate of energy loss. Okay, in other words, that's a Q, as we've been talking about it, per time. Or 640 joules lost per second. Okay. That's Q per second. So, you might ask, okay, well, how much energy am I going to lose in, say, 30 seconds? How much, how much heat am I going to transfer out in 30 seconds? Let's take a look at that number. If I have it in 30 seconds, then that amount of Q is just going to be the power radiated multiplied by the time, and the time is just the 30 seconds. So it's just that times 30. And you can see that's going to be 1800, and that's going to be 19. It's going to be close enough to 2000 if I just multiplied this by 3. Okay, so let's multiply this by 30 and say it's about 20,000. 20,000 joules, which is 10 to the fourth. Okay, so or 2 times 10 to the fourth. Okay, so now the big question is, and we're going to go back to what we learned before about heat capacity. What does that mean for my temperature decrease? Okay, what does that mean for my temperature decrease? So let's go figure out, since I am a basically bag of water, right? More or less. Yeah, there's bones and stuff, but for the most part, our specific heat is going to be near that of water. Okay. So let's just say it is water. And I want to figure out, given that I've just transferred that amount of heat out of me, if I'm a bag of water, what was my temperature drop? Okay. So let's take a look at uh, let's take a look at how much that means my temperature is going to go down. Now, remember I don't know if rules is the right word here, but remember how calorimetry works, okay? If it's a sensible heat, then it simply contributes to this heat loss simply contribute to a temperature change, okay? If there is a latent heat involved, then I have started to freeze, okay? So let's take a look at how much of a change would occur due to that heat loss. All right. So I'll just assume for a minute that it's all sensible. In other words, it's a specific heat problem. Right? So what is delta T for a Q of approximately 2 times 10 to the fourth joules? All right. So we're going to assume that my specific heat, right, that of a person is C of water. And so that's going to be around 4,200 or say 4.2 joules. If I'm using joules, well, I'm going to use kilograms though, huh? So we'll do 4,200 joules per kilogram per centigrade, right? That's all underneath there. If I'm assuming it's all sensible heat, then I can solve for what the temperature change would have been, right? This delta T would be Q divided by M and little c. My mass and my specific heat, and that 20,000 joules. So what's the temperature change going to be? Now, if it turns out to be something like in the centigrades, remember, we'll be in the centigrade. If it turns out to be something like 50, well, then that's problematic because internal, I don't know if you have these numbers off the top of your head, but you know the 98.6 internal, that's on the Fahrenheit scale. Internal temperature, when you take the thermometer reading, 98.6 is about 37 on the centigrade scale. So if I suddenly find that my delta T is 50, I have undergone a phase change most likely, or I am currently undergoing a phase change. And yes, I have frozen. So let's take a look. I'm going to go 2 times 10 to the fourth joules up here for my heat loss, right? It's a loss. Okay, so fine. I'll put in a minus in here. And that way our delta T will come out negative. But we knew that anyways. My mass. Oh, it's not what it used to be. I'll go 90 kilograms because 100 kilograms is 220. I'm not there yet. Huh, I'm trying apparently. So we'll go 90. We'll go 90 kilograms. My C we said was about 4,200, and that's joules per kilogram centigrades. So noticing that the joules are going to cancel, the kilograms are going away. I've got centigrades in the denominator at the bottom, flipping those up, that should work. And so when you look at this is a number that, yeah, that's about 10 to the 2. This is 10 to the 3. And it's a 4-ish times 10 to the 3. Sorry, 4 times 10 to the 5, because I've got the 3 and the 2 down here. So you're noticing this is not going to be a very big temperature change, right? This is going to be approximately, if it's 10 to the 4 divided by 10 to the 5, it's about 0.1 centigrade. It's actually even a little bit less than that based on the 2 and the 4 and stuff like that. So maybe it's even half of this, but it's about that, right? I'm not going to quibble over a factor of 2 in here. So, and yes, I know I changed the 90 into 100 in my head. Even after I said I wasn't 100 kilograms, I probably just should have said that anyways for the sake of keeping my pride out of it. So I'm losing 20,000 joules, and it's only causing my internal temperature or my skin temperature to drop by 1/10 of a centigrade. Okay. What that means ultimately is then that my internals are going to transfer heat out, right? It's going to conduct from my insides to my skin. It's going to reheat me up, and then it's going to lose it again, right? So my internal is going to try and keep me at my skin temperature, which I assume was about 300, which is about 27 centigrade. And so after 30 seconds, I will have only dropped by 1/10 of that. Is that noticeable? you might feel a little chilly, yes, but it's remember, I think I said this at the beginning, radiation is the slowest of the conduction and the convection and the radiation processes. Radiation is by far the slowest. So if you were uh, in a room in which you lost 20,000 joules of energy, you'd probably be like, "Ooh, this is much quicker, right? It's shivering time. In 30 seconds, it would, right? It wouldn't take that long." So if you consider that I have to lose, right, if my internal body temperature is about 37, 36, 37 degrees centigrade, to completely freeze me down to zero, and this, by the way, this is not going to be correct because if you notice, what will have happened, my temperature will have changed, which means my radiation rate will have changed, right? As I'm dropping in the amount of radiation I'm giving off, that means this number here drops. And so my rate becomes lower and lower as time goes on. But nonetheless, you might say, well, it's about 36 and I'm losing, this was in 30 seconds, so I'm losing zero point 0.2 per minute. I'm losing 2/10 of a centigrade per minute. If you multiply 2/10 by 60, that's about a degree. So you're talking about 18 hours or so. If this stayed at this rate, which we know it wouldn't, it would be decreasing. And so it would be slightly more than 18 hours. You might end up about 24 hours. I don't know, just an estimate for total freezing time. So just to see how far we were off, what would be my rate of power radiated if I was 273, right, at 0 centigrade? That number, if I take all the same numbers here and I just put in 273 instead of 300 down there, then I get actually 440. Which is about a 1/3 decrease. So yeah, it'll take longer, right? It wouldn't take 18 hours. It would take a bit more than that. But nonetheless, it's not a quick process. You wouldn't freeze because this is the only way you're losing heat. Okay. So a bit of funsies there. What would be a bit of a problem, of course, is that with no pressure outside of you, um, it turns out that you are porous and you have a approximately 1 atmosphere internal pressure because here we are at the atmosphere and we're doing okay. Uh, if I have a 1 atmosphere internal pressure and 0 on the outside, it turns out that I start leaking. It's yeah, and that's kind of gets gross. So we'll stop that there. You just become a leaky bag of fluid. Okay, so covering all the good bio stuff today. Or no, just in general last time too. All right, so this is how you calculate radiated power. Um, it's pretty, I think, in terms of just figuring a calculation, it's fairly straightforward, right? It's just these three numbers that you need to kind of think about. What's the area? What's the emissivity? How black body-ish is it? And what is its ultimate surface temperature? All right. So, with that being said, and now you are armed with the wonderful knowledge that you could go out into outer space and not freeze. You'd have to try and hold your breath, of course. But, well, you'd be better off holding not your breath, right? Because then you've got all this extra stuff that now wants to go out. So you actually want to exhale as much as you can in order to suffocate. You're welcome. Okay. All right. So at this point, let's go do this. We're gonna go take a look now. I'm going to cheat a little bit, and we are going to talk about the uh, the molecular model of matter, the atomic model of matter. So this is not strictly a classical thermodynamics subject. Nonetheless, it does show up in this class because we're not studying strictly classical thermodynamics, and I think uh, where my uh, that's where I start to have kind of like a sad face. But nonetheless, we're going to talk about the molecular model of matter, and I told you that the idea of thermal expansion, gave us information that um, the bonds between atoms are not spring-like, or between molecules are not spring-like. They kind of are a little bit, but ultimately they're this other-looking thing, right? So if you remember, uh, the spring potential is just a parabola, whereas this fellow comes up with a potential that looks kind of like this, right? This is a model of molecular bonds. Also known, if you are interested, also known as the 612 potential. And the reason for that is because it's modeled as a function, which is a over x to the 12 minus b over x to the 6. So it's the 612 potential. Now remember, it did look a little bit spring-like right down here, right? It is bowl-shaped like a spring right down here. And let's just check to see if you can actually see that. You kind of can. All right, I'll re-ink this thing. Right down in here where the energy is low, it is spring-like. But then as you increase the energy, which is to say you increase the temperature, you start going to higher and higher amounts of temperature. Then you start seeing that the vibration looks right. It's just all I'm really thinking about is a ball just rolling along a shape like this. No friction, of course, right? So it's going to be spending a lot more time out here, which means its average position has shifted from here, which is the lowest, to over here as it moves, as the energy moves upwards, right? When the energy reaches zero, of course, you have completely dissociated the two molecules or the two atoms or whatever it was, because now they have zero potential, and that's right, a marker uh, of no interaction between the two things. Okay, so that this thing asymptotes up towards the zero line. And you can see that as I move the energy close up to that, then it's going to be spending a lot of time over in this area, and then it'll it's going to be kind of like a roller coaster, dude. All right. So knowing that this is our model of matter, what can we say about the ideal gas, which of course has no bonds? So this has all been just that was what. All right, let's take a look at the molecular model of the ideal gas. Okay. And I do, and I'm sure I've said this at least 2 to 3 times already, but I'm probably going to keep saying it because it does upset me. This is not strictly classical thermodynamics, which this is supposed to be a class in thermodynamics, but really it's not. It's a class in thermodynamics and some other useful information for people who maybe want to go into some type of technical career. So that's really what it is, and I have to start thinking about it that way. All right. An ideal gas, remember, if I were to graph the potential of it, U of R for an ideal gas would just be, say here, a spike that goes up to infinity, and then the rest of it is zero. Did I mark my R up here? There's that R. Okay, it goes up, it's a spike that goes up to infinity because basically what's happening here is I have oh, I didn't bring in the darn. Well, anyways, imagine that these are two atoms of an ideal gas, right? And they're moving around. They don't hit, I mean, they don't interact until they hit, and they don't hit until you'd have to imagine these are spheres. They don't hit until their centers are a full diameter apart. Okay. In other words, you'd have the center of one of the molecules or atoms here and the center of the other one here, so that, right? It looks like that. When they hit together, the centers are a diameter apart. Okay. So let's do this. We're gonna go take a look at if we do consider the ideal gas as a set of basically non-interacting billiard balls, right? They're hitting each other, right? And they're moving, well, they're hitting, so they interact then. But all other times, they're not getting pulled on by any type of potential. So let's imagine if we can figure out what the behavior looks like if I had a whole bunch of these and they were really tiny and they were smashing against things. In other words, let's try and use our ideas of 4A mechanics, okay, to try and figure out and predict what a molecular model might look like if we assumed the simplest possible thing, which is they are an independent set uh, of basically infinitely rigid spheres that are hitting the sides of an infinitely rigid container, right? I have a sample of gas in this room and the molecules are hitting the walls. See, this is the thing where you already know this is happening, but take yourself back to the 1800s. Nobody knew a damn thing about molecular gases and why is this happening? What's that, right? They're still trying to figure stuff out. And one of the goals of physics is to try and use a theory to explain and predict. So let's use our mechanics, our Newtonian mechanics, to try and say, all right, I'm going to apply this now to my model, which is a set of completely non-interacting rigid spheres that are moving around fast and they hit the sides of a container. All right, so a couple of assumptions. Like I said, we'll assume everything is infinitely rigid and we aren't going to worry about deformation. We're not going to worry about leaking. The collisions between these things are perfectly elastic. Everything's really nice and ideal. So this is how this is uh, exciting because this is how you apply a theory to make a model to make some predictions. All right, so let's get rid of this. And so let's take a look at a container, right? Here's the wall of a container. And remember, I'm assuming this is infinitely rigid and that the collision is perfectly elastic. Okay. So let's look at the behavior of one of these rigid spheres, okay, that's moving around and it bounces off the wall. Let's take a look at just the behavior of one of them, and then we'll try to go to many of them, right? So let's suppose that I have one here. Okay, here's my infinitely rigid gas particle, and it's coming up here, right? It's got a velocity this way. So it's going to hit there. And bounce off that way. Well, that didn't quite seem, well, the angle should be maybe a little bit better than that. But anyway, this angle should be about the same as this angle. right? It's perfectly elastic. Okay. Okay, so if we just look at this from a Newtonian mechanics sense, okay, I'm going to look at the ball. This is exactly like taking a billiard ball and thinking about it hitting the bumper. This is all this is, right? So I'm going to break down my velocity into its two components, one of which is going to be this way. I'll call that my Vy because we always have x going to the right, yeah? So we'll do xy like that. And I'm going to have my Vx, which is going this way. All right, and I'll call that Vx, well, it doesn't matter. I don't need to call that Vx initial because when I get over here and I look at this thing, here's Vx final, right? And here's Vy. Now, in the collision, it's perfectly elastic and perfectly rigid, so Vy shouldn't change. There's no reason for Vy to change. If you notice, what is the thing that changes is Vx, and that means that the force must have been directly orthogonal, or say normal, if you like, to the surface. Oh, it's like a normal force. Ah, wonderful. I think we learned about those. So we're going to take this normal force to have acted directly towards the right in what I would have said is the plus x direction. Okay. Now, since this is a perfectly elastic collision, how big is Vx final compared to Vx initial? Let's see, force exerted. I'll just call this force F. Right? So the force, if I drew the particle in contact with the wall, I would have drawn a force directly to the right. All right. Oh, so let's call it force X. Force X. Force X should be the change in momentum in the X direction divided by the time interval during which the collision occurred. That's just straight Newton's second law right there. So our goal here is to then deduce what is the change in momentum in the X direction. Well, in order to do that, we have to make a relationship between Vx initial and Vx final. Now, we go back and say, this is a perfectly elastic collision. Therefore, Vx initial and Vx final should be exactly the same. And my change in momentum would then be m times Vx final minus m times Vx initial. Alrighty. Since these two are the same, oh, look, the force is zero. If these two are the same, you can see they're subtracted, so I guess there's no force. Does that seem right? What is it that I'm missing here? If these are both equal to Vx, shouldn't I just get zero? Well, yes, if they were both equal to Vx, but you can see that they aren't. How do we see that they aren't? Because one of them's pointed that way and one of them's pointed that way. And we remember that momentum is a vector quantity, and therefore I need to include a minus sign in the initial velocity because the initial x velocity is towards the left. So really then this comes out to be one plus the other one because I get the two minuses in here. Oh, it makes sense now. Now I get it. All right, so this momentum is 2mvx here. That's the change in the momentum, and it's per time. M is just the mass of the particle that's hitting the wall. And this is wonderful. Isn't that great? Well, no, because that's only for one particle hitting a wall during a small time interval. I'm going to assume that we actually have a lot of these. And yes, in the 1800s, they did know what Avogadro's number was. And they knew that that was a significant indicator of how many things there are in the microscopic world. So we have to think about there's 10 to the 23rd of these things hitting. Okay. So this is just The force, this is just the average force of one particle hitting the wall at a time. What about n of them hitting the wall? If I want the average force total, the total force, I have to take the force from just one of them and multiply by how many collisions I have. Okay, I'm going to call that n, capital N with a collision, number of collisions, right, times Fx. Fx being this thing. Okay. Well, now I need to go in and figure out, well, how many collisions am I having? Remember that there's a time interval, right? And during the time, but it's a different, I've got two different time intervals. But I have to think of these things are traveling with a certain speed, right? Which I said was Vx. Now, what I want to think about is any particle of gas that's near enough to the wall such that it would have a collision with it in a certain amount of time, then let's just say that that's the number that could possibly be getting hit by the wall, right? So that would mean if I'm going to just kind of draw an extra picture down here. Okay, my wall is still here, but now imagine that I've got kind of a boundary here. Okay, I've got a boundary over here. How far away is the boundary? Well, the boundary, let's say, is Vx times some delta t here. Okay, that's how far away the boundary is. So during delta t, any particle that's in here has the chance of hitting the wall. And by the way, there's lots of particles in here, right? Here's the ideal gas. Right? It's got lots of particles. And what I'm seeing is that, and this, by the way, is only part of the container. The container might go all the way out here or something like that. But there are particles within this distance which are going to hit the wall. Okay. Now, does every particle have a velocity in the x direction of Vx? No, they don't. But that's okay because some of them are closer and some of them are further away. And okay, so on the average, maybe they have Vx. Okay, so these things are moving around. So the question here is, what is this number? This number, the number of collisions that's happening, right? That number of collisions is how many collisions are made during the time of delta t. That's what my n collisions is going to be. All right. Now, in this sample of gas here, I'm going to assume that this is at thermal equilibrium so that there's no tendency for heat transfer, right? If in one direction or another. In other words, if there is heat going this way, then there's equal amount of heat going this way, right? Or right, if there's an energy transfer, it's going to get transferred back. There's no net transfer one way or the other. It's a zero total net. Which means that from this point of view, what I can say is that of these particles that I have in this volume right here, it's reasonable to say half of them are moving towards the wall and half of them are moving and will not hit the wall and moving the other way. So in the time delta t, I can expect about half of these will hit because they're moving to the left and the other half are moving to the right and they won't hit. Or maybe they already did and we don't care, okay? So that's where thermal equilibrium comes in because I can say that that not all these gas molecules are just coming this way and going to smash into the wall. Well, would be a little weird, right? It should be more randomized than that. All right. So we'll assume that half of these are moving towards the left. Okay. Half of the particles are moving to the left. All right. Okay, that's good. I can get rid of this. Okay, so we just have to count up how many those are. How many particles are moving to the left? Okay. So what I'll do is I'll say, okay, I'm going to take the total number of particles per volume that I have, right? The total density. Remember, this is only a small slice of the container. The container's much bigger than this. And this is just the number that are moving to the left with and that are this far away from the wall. Okay. So my number of collisions should equal now I'm going to take the total density, right? The total N over V of all of these things, and I'm just going to multiply by however much are in this volume. Remember, this volume is huge. I just want the number of particles that are in this volume. And then I want to multiply that number by a half, because I'm assuming half of them are going this way and half are going that way. All right. So if I take the total density, N over V here, right? This is the gas density. Now I'm going to multiply by this volume right here. And I'm just going to call that the volume of colliding particles. Right? And then I need to take that and multiply by half. So I'm going to throw the half out in front here. And I'm going to have that. Okay? Okay. What is the volume that contain potentially colliding particles? Okay, well, that volume has a distance this way, which we already know is Vx times delta T. This volume is equal to Vx times delta T, right? Remember that if it's a V with, I don't know if you can see that. I'll try writing it bigger. I'm trying to remember to write bigger. Apparently not succeeding. Vx times delta T. Now, if it has no bars on it, it's a velocity. If it has the bars on it, it's a volume. You're welcome. Not everybody does that. This is what I do for you. I also need to know what is the cross-sectional area, right? What, like how, if I were to look down on this, what kind of area am I looking at? All right. So let's just call that an area A. Okay. We'll go ahead and assume that this is a cube. Maybe it's going to be easier to consider if I have a cube with gas particles in it and I'm looking down this way, that would mean it's the same cross-sectional area on any face. Okay. So this is the volume of colliding particles. This is the density and the number of collisions. So the total number of collisions that I'm making should equal 1/2 capital N. Now, this is the number of particles. This is the number density of particles, N over V, times A Vx delta T from the volume here. And what I'd like to do is just take this delta T and swing it over underneath the number of collisions so that I have an idea of how many collisions are we having per second. The number of collisions divided by the time. All right, so that just means I've taken this thing and I've swung it over here, so it's no longer here. And now it's equal to 1/2 N over V times A Vx. Put that in parentheses so you're not messing that up. All right, like this. Okay, good. So we're just going to erase this right here. Oops. Kind of wish I had left that up there because now I could remember what that was. All right, so look here. What do we have? Where was I? Oh, yes. Okay, so now I'd like to figure out the total net force. The average, or no, I call it average. Sorry. The average total force that is required on all of these particles that are hitting, right? So it's kind of the average total force that the wall supplies. So that was 2 mvx divided by delta t, right, times n collision. But I'm going to move the delta t over to underneath the n collision so that we have this. And I already have the expression for that now, which means I can just say it's equal to 2 mvx times this thing down here, which is 1/2 capital N over V, A and Vx. All right. Okay. So with a little bit of shenanigans, we have gotten to this point. Remember that if this is a gas, the total force is not really a measurable quantity. So nobody really cares about that. But what we do care about is the pressure that's exerted. Remember that the pressure, P, remember this is now P with a foot on it. Aha, see, I got it last time because I had P with the momentum. Now I've got P with the pressure. Now I've got the foot here. The pressure P is the force per area. And that means all I have to do here is take the net, the average total force, and I have an area stick, and it's right there. So I'm just going to swing that underneath the force here, and then I'll have an expression for the pressure. I'll have 2. I'm going to also rewrite it in a slightly more suggestive manner. I have 2 times N over V times 2 N over V times 1/2 M Vx Vx. That's Vx squared. What does that thing look like? I'm pretty sure we've seen that before. See, this is just a Fourier analysis. There's nothing, well, if you really like to think about force C and the pressure or the gas density or something, sure. But really, this is just a mechanics analysis, right? This is just straight Newtonian stuff. This here's the translational kinetic energy, but it's in the X direction, right? It's just this one. That looks like the KE. Okay, remember that I was talking about the average force. So really, if I'm looking up here and I'm thinking about the average force, remember I kind of slipped this in a little bit ago. I erased my picture, but not every dot is going to have the same velocity towards the wall. There's going to be an average, right? So really what I should be doing here is taking the Vx average, right? But it's not Vx, it's Vx squared. I should be taking the square of Vx, right? And saying the average of that thing. All right, so really what we need to use is Vx squared. And these bars mean average. Or the brackets, I guess, mean average. Okay. So now I'm going to ask this question. If I had a cube of gas, right? I just happened to select the left-hand wall. What if I looked at the top wall? Would I be able to do the same analysis? Would I be able to say, oh, there's some particles here that are moving up, some that are moving down? Let's say half are up, half are down. I'm going to take a small volume of those particles that are going to reach the wall in a Vy delta T. Wouldn't I be able to do the same thing? And what if it was one of the front faces or the back faces? Wouldn't I be able to do the same thing? So we don't want to give preference to the X direction here, right? We want to say X, I could have done Y, I could have done Z. It would all be the same thing, right? So really, I'm going to say that there's a total velocity. This is a V squared right? The average V squared should be an average of Vx squared plus Vy squared plus Vz squared, like this, right? And each one of them should be 1/3 of all of the total, right? It should be, they should all be equal. So Vx squared should equal 1/3 of V total squared, right? V squared average. Remember, I'm taking the V squared and then the average of that. Because if I take the V and then average it, it should be 0, right? There's equal numbers moving that way as there are moving that way. So why would there be an average velocity? It should be 0. So I'm taking the square of the average. No, I'm taking the average of the square. Got it backwards. Okay, thanks for catching me. No problem. All right, so all I got to do is take this thing here, put it up to there. I've got a 1/3 coming in here. Vx squared is 1/3 of V squared. I'm kind of running out of time here, so I think maybe I'll have to finish this up next time. But what we're getting at here is I'm going to come up with an expression for the pressure in terms of a kind of a molecular, like a particle view of what's going on. Let me just make note that I am finishing here so that we can move on from here. But you'll see that I'm going to get a 1/3 up there, right, from the Vx right in here. Okay, so you'll see that. And we'll go up and do a few more shenanigans next class, but I think that's going to be about it for today. And we will pick this up on Wednesday. That's tomorrow. And then labs, please have those labs written up and submitted at some point tomorrow. Like I told you in the lab, it's fairly straightforward of a lab. It's no huge data taking. I guess maybe I wasn't clear in the lab itself. You don't have to wait for the thing to come all the way to room temperature. Just take 15 to 20 data points in the tracker and see how it goes. And then you can assume after 5, if you can get a good curve fit, then you can know what the time constant is. And then, like I said in the video, you take 5 time constants and you can assume you've gotten to equilibrium by then. Alrighty, so good luck with that. As far as this goes, I will see you tomorrow and we will move on from here. All right. Happy rest of your hopefully sunny day, folks, because it is a sunny day here in the Central Coast. So we will see you then. Bye for now.